A bombshell just dropped on the astronomical community, but it wasn't from space. While the West's most powerful telescopes were blind, Chinese observatories released crystal-clear images of the interstellar comet 3I Atlas. This isn't just about a new comet, it's about a seismic shift in who controls our view of the cosmos. This sudden pivot in the observational balance is stirring more than scientific curiosity. It may signal a new era in how we monitor these alien visitors. Let's explore this together.
Strange composition.
What if a visitor from another star system was a complete chemical stranger? That's exactly what we're seeing with 3I Atlas. This object is unlike anything that originated in our solar system. Observations so far have revealed a bizarre chemical fingerprint. Its coma, the gassy envelope around its nucleus, is dominated by carbon dioxide emissions, with a CO2 to water ratio far higher than any comet we've ever seen. Data from the James Webb Space Telescope confirm this, showing a CO2-rich coma with only trace amounts of water. For comparison, a typical solar system comet might have a CO2 to water ratio of around 10%, but initial findings for 3I Atlas hint at something dramatically different. This composition tells a story. As explained by cometary scientists like Martin Cordner, such a high abundance of CO2 suggests the object formed in an incredibly cold region of its home star system, a place far colder than our own Kuiper Belt where even carbon dioxide gas freezes solid. The presence of irradiated ices and complex organics further deepens the mystery, suggesting its surface was battered by high-energy cosmic rays for millions of years as it traveled through the interstellar void. This isn't just a slight variation, it challenges our fundamental models of planet formation, which are almost entirely based on the architecture of our own solar system.
Telescopes go dark.
But what happens when our best eyes on the sky suddenly close right as this once-in-a-lifetime visitor is putting on its best show? This isn't a hypothetical fear, it's the reality that just unfolded. Major observatories like the Hubble Space Telescope, the JWST, and the European Southern Observatory's Very Large Telescope are the workhorses of modern astronomy. They provided the critical data that shaped our initial understanding of 3I Atlas. But these are incredibly complex machines. In mid-2024, Hubble had to switch to a single gyro mode, a necessary fix that nonetheless impacts its efficiency and scheduling flexibility. The VLT's four main telescopes periodically go offline for the recoding of their massive 8.2-meter primary mirrors, a delicate process that can take a telescope out of commission for weeks at a time. Even the JWST has faced challenges with its instruments. The transcript suggests several of these key Western telescopes went offline just as the comet's activity was evolving, creating a critical data gap. This isn't just bad luck, it exposes a systemic vulnerability in a highly centralized system, a single point of failure that can blind us at the worst possible moment.
China steps in.
Nature abhors a vacuum, and so does 21st century science. Into this observational gap, a new power has stepped in. China. Over the past 2 decades, China has invested massively in its astronomical capabilities, a strategic push outlined in its long-term science and technology development plans. The images of 3I Atlas didn't come from old equipment. They came from facilities like the Purple Mountain Observatory and the Xinglong Observatory, equipped with modern wide-field survey telescopes. These systems are capturing both the comet's detailed structure and the background star fields with stunning clarity. This capability is set to explode with the launch of the Zhangtian Space Telescope, a 2-meter observatory with a field of view 300 times larger than Hubble's, capable of surveying 40% of the entire sky over its 10-year mission. At a time when Western facilities are dark, observers in China are providing fresh frames of the coma and tail structures. This isn't just about filling a data gap, it's a strategic move that gives them a window to exercise scientific leadership. They have seized a historic opportunity, demonstrating that their long-term investment in astronomical infrastructure is now paying off on the world stage.
Data controls narrative.
Here's what really matters. In science, the person with the data writes the first draft of history. By capturing and publishing the first high-quality images of 3I Atlas during this critical window, Chinese teams will inevitably shape the scientific narrative. These initial observations become the reference points for all subsequent research. Think back to 1995, when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b. Their data, showing a massive planet orbiting its star in just over 4 days, created the hot Jupiter category and dominated exoplanet theories for years. Similarly, the Chinese images might be the first to identify key features in 3I Atlas, setting the agenda for the entire global community. Their interpretations, published rapidly on preprint servers like Arxiv, will gain significant mindshare before the formal peer review process is even complete. In a scientific ecosystem where reputation and early access are paramount, this gives Chinese teams a powerful boost, allowing them to take the lead on developing the first credible models of this alien object's behavior and origins.
Data sovereignty.
This brings up a bigger, more complex issue. Who owns the data from another star system? For decades, Western astronomy, particularly NASA, has championed open data through archives like the Planetary Data System. This democratic approach allows any researcher, anywhere, to download and analyze raw data, fostering independent verification. However, this is not the only model. The European Southern Observatory often has a 1-year proprietary period, giving the original observing team exclusive access to their hard-won data. As China's infrastructure grows, it can choose its own path. Data becomes a tool of soft power. If institutions like the National Astronomical Observatories of China control access to their 3I Atlas data, it could create data silos, complicating the creation of a complete global picture of the comet. The decision to release the raw FITS files, the standard format for astronomical data, complete with vital metadata, becomes a strategic choice that impacts not just science, but scientific diplomacy and the very culture of international collaboration.
National prestige.
Let's be clear, observing the cosmos is about discovery, but it's also about power. Space science is deeply intertwined with national pride and global influence. China has long used its space program to showcase its technological prowess. The Chang'e 5 mission in 2020 returned 1,731 grams of lunar material to Earth, the first sample return in over 44 years, a massive prestige victory. Releasing key images of a rare interstellar wanderer like 3I Atlas, especially when others cannot, is an equivalent statement in deep space science. The media narrative practically writes itself. China steps up when others falter. This resonates far beyond academic circles, bolstering national prestige and justifying massive government budgets for science and technology, creating a self-reinforcing cycle of investment and achievement. It reframes the 21st century space race as a contest not just of exploration, but of knowledge generation, positioning China as a leader in a frontier domain previously dominated by the West.
Infrastructure fragility.
Ultimately, the 3I/Atlas incident exposes a fundamental crack in the foundation of global astronomy. For decades, the field has been shaped by a heavy reliance on just a handful of powerful, Western-funded flagship observatories, many of which are, geographically concentrated in places like Hawaii and Chile. But honestly, this model is fragile. This event serves as a stark reminder that our global network for monitoring the sky is just not robust enough. It really highlights the urgent need for diversification and support for projects like the Vera C. Rubin Observatory in Chile. Once operational, its 8.4-meter mirror and 3,200-megapixel camera will conduct the legacy survey of space and time, scanning the entire visible sky every few nights. This kind of continuous watch is a direct answer to the problem of missing transient events. The incident also underscores the importance of geographically distributed networks like the Square Kilometre Array, ensuring that no single point of failure, be it technical, political, or weather-related, can blind humanity to a critical cosmic event.
Verification questions.
New data is thrilling, but it arrives with a critical question. Can we trust it completely? The scientific process is built on verification, and integrating the Chinese data on 3I Atlas isn't simple. Are the new images calibrated in a way that is fully compatible with previous data? To answer that, the global community needs the raw FITS files and all associated calibration frames, the darks, biases, and flat fields required to remove instrument signatures. Without these, it's impossible to perform accurate photometry, the measurement of the comet's brightness, to see how its activity is changing over time. Furthermore, high-precision astrometry, or the exact measurement of the comet's position against background stars referenced by the Gaia catalog, is crucial. This data is needed to refine 3I Atlas's hyperbolic orbit and search for tiny non-gravitational forces caused by outgassing. Full transparency, including sharing data reduction pipelines, is the only way for the results to be independently replicated and universally accepted by the scientific community.
What the images reveal.
So, what could these Chinese images of 3I Atlas actually show us? They are far more than just snapshots, they are dense with physical clues. Astronomers like David Jewett at UCLA, who co-discovered the Kuiper Belt, would meticulously analyze the coma for structure. A faint jet, perhaps only a few arcseconds long, could reveal the spin axis of the nucleus and point to a specific active region. By measuring its surface brightness, one could estimate the dust production rate in kilograms per second and compare it to well-studied comets like 67P Churyumov-Gerasimenko. The transcript suggests that some releases show brightness falling off more rapidly in certain sectors, hinting at asymmetric outgassing. Most excitingly, a rapid sequence of images might capture a fragmentation event. If the nucleus were to split, as Comet C 2019-Y4 did, these observations might be the only record of it happening, providing invaluable data on the structural integrity and tensile strength of an object from another star system.
Global wake-up call.
Bottom line, this event is a shock to the system of global astronomy. It's a wake-up call on multiple fronts. First, it forces a reckoning with the fragility of our observational infrastructure. It will likely accelerate pushes for more distributed networks and formalize coordination through frameworks similar to the International Asteroid Warning Network. Major observatories will likely reevaluate how target of opportunity time is allocated to ensure that high-priority interstellar objects get immediate coordinated follow-up. Second, it recalibrates the geopolitical landscape of space science, forcing Western institutions to forge new alliances and advocate for more resilient, internationally managed observatories. Finally, it shines a light on the changing nature of discovery itself. It's becoming less about a lone genius at an eyepiece and more about managing vast, complex, and sometimes fragile global systems of technology, data, and collaboration. The 3I Atlas event is a powerful case study in this new scientific reality.
What do you think this shift means for the future of astronomy? Is this increased competition a good thing for science, or does it risk fragmenting our global community? Let us know your thoughts in the comments below. We want to hear from you. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the cosmos. Thank you for watching Future Facts.